Okay, in this video we're going to start talking about energy balances and non-isothermal reactor design. As you probably can anticipate, most reactions are going to consume or generate heat as they occur, and therefore you're going to either need equipment in order to control the temperature at the desired setting, or you're going to need to be able to anticipate in the absence of temperature control what that temperature will do and how it will affect the reaction processes happening inside the reactor. Energy balances are something that you guys have all seen before. You know that it's a balance of internal energy, heat, work, enthalpy of streams flowing in and out. Usually we are not going to need to think too much about work, but there are a few examples where maybe work will come into play. So this is our generic energy balance. We have a time derivative of the internal energy is equal to heat flow coming into the reactor, work done on the reactor contents, enthalpy flowing into the reactor, and enthalpy flowing out of the reactor. So this is the little diagram here to sort of keep in mind how these balances all play into things. And of course, this is going to be valid for all the reactors that we're going to encounter. So I want to talk a little bit about sign conventions here. So when you look at this equation, it's important to keep in mind what each of these terms means and not mix up the signs. Okay, so if you have heat being added to the reactor as depicted here, a little flame below our reactor pot, this is going to give you a Q term that's greater than 0. If you have compression of the contents of the reactor, for example, this is work being done on the contents of the reactor, and it's going to give you a work contribution that's larger than 0. The work term, it's going to include shaft work and stirring and grinding, things like that. Now, while it does include these things, it's also true that in most cases we can get away with ignoring them, unless it's really a major contributor to how the reactor works and what it's doing. In most cases, we're not gonna have to worry about these contributions. You know, if you put a stir bar into your reactor, you can pretty safely ignore the dissipative work done by that stir bar and how it does make a contribution to the thermal energy inside the reactor, but you can usually ignore that. The work term does include boundary work. For example, the compression example that I just showed above, this one right here. So this is of course what's happening in a piston chamber. Now this term is never in steady state form, right? So it's going to be useful in most cases to combine this term with the du dt term. Okay, so both of them are going to be things that are going to be changing in time, and we can often combine those two fruitfully. W also does not include the work to change the density of the inlet and outlet streams. And the reason for that is that those contributions are already included when you write down the enthalpy of the stream flowing in and the enthalpy of the stream flowing out. More notes about what's included and what's not. It's often useful to remember that the internal energy and the enthalpy are state functions. For example, if we consider a reaction in a batch reactor, then we might imagine that the real temperature versus time and x versus time curves plotted against each other might look something like this. We've got a temperature axis on the vertical and a conversion axis across the bottom, and we can start from an inlet condition at some temperature T0 and conversion 0. And if you follow, the temperature in the reactor might initially rise for a while, if this is an exothermic reaction, for example, and then as the reaction slows down, the rise in temperature continues but slows down a bit, and you end up over here. Of course, the shape of this curve depends on whether you have a heat exchanger or whether it's adiabatic operation and things like that. What we can often do is imagine breaking this process into two distinct portions, right? So we can imagine that we modeled it as a step first where we heat all of the components that are in the reactor, so nothing has reacted yet. These are the inlet flows, the inlet contents of the reactor, multiplied by the heat capacities and multiplied by the temperature change. Okay, so that's a contribution to the enthalpy right there. And then we can start from this point, and we can imagine that it all happens at constant temperature, that the reaction happens, and we convert all the way to our final value. Okay, so that's another contribution to the enthalpy that has to do with conversion and the enthalpy of reaction. And then to get the overall change for the process going from in to out, we just have to add those two contributions. Of course, we don't have to do things in that order. We can also react everything first at the inlet temperature and then and then include the contributions to heat everything up at the outlet conversion. So this is the outlet composition going from temperature T naught to T now. And that gives you a different way to break apart the two contributions to the overall enthalpy change. Okay, now after all that discussion about enthalpy of the streams flowing in and flowing out, we're going to work on batch reactors where we don't have streams flowing in and flowing out. And so now our generic energy balance equation, those H in and H out terms drop away, and we have du dt is Q plus Wc. So the heat and the work terms, the only things that we have to worry about here. Now the little diagram here, you can think of this as happening inside a balloon. So you've got some internal energy of the gas inside the balloon or a liquid. And there's maybe heat coming through the walls of the balloon to heat the reactants. And then there's an internal pressure times a dV dt. So I want to emphasize that this is the internal pressure, right? So in some cases like this one, the internal pressure and the outside pressure will be different. Okay, so the compression work involved here, we have Wc is minus P inside dV dt. If you have a chemical reaction that's inflating this balloon, for example, then that would be something that you would definitely want to include. So if this is an expanding balloon, then dV dt is going to be positive, and that's going to give us a Wc less than 0, which means the balloon is losing internal energy through the work that it's doing on the surroundings. Okay, it's having to expend some of its energy to do that work. All right, so now we're going to combine these time derivatives. So the Wc term is becoming this thing, and then we move it over to the left-hand side so that we can combine it with the du dt plus P dV dt, and now that's just equal to the Q term. Now, I'm going to remember that H is equal to U plus PV. So I can go through and I can compute the dH dt is going to be a du dt plus a P dV dt plus a V dP dt. Okay, and if I now plug that in and isolate the part that depended on U, du dt, I can now get rid of the du dt in favor of dH dt, and now instead of a P dV dt term, I have a minus V dP dt term. Okay, lots of dPs and dVs. So this is just equal to Q. And now what we're going to do is to go back and try to write this differential change in the enthalpy as some coefficient times the dt plus another coefficient times the dP. Now, maybe you guys are thermodynamics whizzes and you know these things by heart, but I have to start from scratch and go back and do them each time. Okay, so this is complicated, but you can see this done in the typewritten notes on the web. And what you end up with is that dH is a total heat capacity of the contents. You can write this in many different ways. Here, for convenience, I've written it as a volume times a heat capacity on a per volume basis, that's the little hat above this thing, times dt, plus 1 minus alpha times T. Alpha is this coefficient of thermal expansion, and then that gets multiplied by VdP, plus the sum over all the components in the reactor times their partial molar enthalpies, times dNi. Okay, so times the sum over all the components in the reactor times their partial molar enthalpies multiplied by the differential changes in the number of species in the reactor. So this is going to be related to reactions, right? The only way we have things in a batch reactor changing the number of things that are in there is because they're being consumed through our reactions. Do this right now in terms of extent of reaction. It's pretty easy to see how this works. You could do all of this accounting in terms of conversion too, but this is particularly easy to do for extent of reaction. So I have the partial molar enthalpies times the differential changes in the number of species of each species, I. And I could rewrite that by thinking about the extent to which each reaction K goes forward, differential extent of reaction d xi K, and multiply that d xi K by a sum over all the species in the reactor, the stoichiometric coefficient for that species in the reactor, times the partial molar enthalpy of that species in the reactor. Of course, I can replace that sum over stoichiometric coefficients times partial molar enthalpies for each reaction by the heat of reaction, the enthalpy of reaction for the kth reaction. And then you see that second sum really drops out, and you end up with just d xi K sum over the heat of reaction for reaction K. Okay, so this last term that appeared here in our expression can be identically replaced with this much more convenient thing that has to do with my enthalpy of reaction terms. There's a few definitions here that might be helpful. That alpha, 1 over V dV dt at constant P, It's a coefficient of thermal expansion at constant pressure. And then this one is a constant pressure heat capacity on a per volume basis. So this is really just a general thermodynamic relation. We don't have to be working with a batch reactor to make use of this. But now we're going to begin to think about what this does in the batch reactor setting. And we have a differential extent of reaction can be written in terms of the instantaneous reaction rate times the volume of the reactor times the dt. So if I plug this in for that piece right there, and I put all of this together, so remember that this becomes my differential extent of reaction. So now I've introduced something that has to do with my reaction kinetics. I have replaced these differential changes in species numbers with the differential extents of reaction and heat of reaction terms, and it all goes into here. Okay? So if we now take what's left and we put that into this equation, which was my energy balance for the batch reactor. This guy didn't say anything about Q's. We put all that together, we end up with this equation right here. This one can be simplified a little bit. You notice there are V's in every term on the right. We can now divide everything through by V. And a couple of terms cancel. This one cancels with the one in this parentheses here after multiplication by the V dp dt. And you end up with the heat capacity multiplied by the derivative of the temperature with time minus the expansivity factor multiplied by the temperature times the dp dt term plus the sum over all the reactions that are happening times the reaction rate times the heat of reaction for that kth reaction is going to be equal to Q over V. So this is a general equation. Again, this is valid for all of your batch reactor situations. And we can now further break this down into two cases that arise very commonly. Those are that you have constant pressure, dp dt equals 0, or an incompressible fluid. Both fall into this one case. And now this big equation simplifies into this smaller equation that is coming from the fact that when you have an incompressible fluid, this expansivity factor is also equal to 0. That's not trivial. You have to go to a thermodynamics text and review your Maxwell relations. For example, this work is done in Smith and Van Ness and Abbott on page 187 of my ancient edition. A consequence of this assumption that you have incompressible fluids that gets rid of the alpha factor as well. In that case, you end up with the heat capacity times the derivative of temperature with respect to time. We only have our reaction enthalpy terms and multiplied by their rates is equal to Q over V. Now the other case is when you have a constant volume reactor and you also have compressible ideal gas contents. Okay, things are going to be really complicated if you have non-ideal gases. All right, so but if we have this compressible gas situation, then we take the heat capacity at constant volume times dt dt, sum over all the reactions happening. There's a heat of reaction. There's a PV correction in here that accounts for the RT factor multiplied by the number of molecules generated per reaction event. This is the same delta that we've used since we were back doing the stoichiometry stuff. So for example, if you have A plus B going to 2 molecules going to 1, you end up with a delta of -1. And then all of that gets multiplied by the kth reaction rate. And then that's equal to Q over V. Okay, so these are two very general equations. You can, when you start one of these problems for a batch reactor, I really recommend you go back and you see which one of these two cases you can use.